Good morning, good afternoon, and good evening. I'm Tom Concolino, and I'm here with our presenters, Aya Takase and Angela Criswell.
Hi, everyone.
Thank you all for attending Rigaku's virtual workshop. So this is the first of 3 sessions in our deep dive series on digital rock analysis. This session will be taking place in the lab with Aya and Angela reviewing in real time how to develop a scan for rock and mineralogical samples. They'll also offer their thoughts on dealing with the unique challenges of performing CT experiments on these types of samples. So please note, if you missed any of the previous webinars, you can view them on the Rigaku website. We also want to welcome Arne Jacob, application engineer at Math to Market, as a guest panelist. He'll be able to add additional thoughts and will also be available to answer questions throughout the session. Thanks for joining us, Arne. But before we start, a few housekeeping items. As far as today goes, this is an interactive session, and we'll be taking your questions live during the session. We'll answer some of those questions during the live sample scans, so please don't wait until the end to ask. And as usual, please submit those questions via the Q&A button at the bottom of your screen. We won't be monitoring the raised hand function, and I'll be posting relevant links in the chat window. Now, we'll be trying to answer as many questions as we can during the session, and we'll respond to any unanswered questions after this session is complete. If for whatever reason you have difficulty viewing the workshop live, please note that it is being recorded and you'll be able to view the recording beginning tomorrow. Okay, and with that said, I'll turn it over to Aya and Angela.
Thanks, Tom and Ian, and thanks to everyone for joining us to our workshop. We are presenting live from our office in the Woodlands, Texas. And today we're starting a new series, Deep Dive into Digital Rock Analysis. Now, before we start, I have a confession to make. I'm actually relatively new to the subject too. And my plan is to share what I've learned in the last 6 months or so in a condensed manner so that you can save some time to learn what you need to learn about digital rock physics and analysis. And because I'm new to this, we invited Arne to join us so that he can provide his expertise and answer some of the questions you might have. So this is a 3-part series, as Tom mentioned. In the first part, we're going to talk about the data collection. And in the second part next month, we will cover segmentation and some of the property analysis. And in the third and the last session of the series, we will look into digital rock simulations. But for today, we're going to focus on data collection. And things we're going to cover today include how to assess the required resolution. You have to know what resolution you need depending on the sample you're looking at so that you can do accurate simulations. And resolution is not the only thing you have to think about when you think about the CT image quality. So we will cover how to collect high quality CT images. And lastly, once you have a scan, you probably want to evaluate the quality of that scan. So you will also learn how to evaluate the image quality so that you can do, again, an accurate digital rock analysis. As far as tools go, we're using the CT Lab HX. This is the benchtop micro CT scanner, and you will be seeing quite a bit of this system today. And as far as the software goes, we're going to use Geodict by Math to Market. And we're going to use this software only just tiny bit at the end of this session, but you will see this whole lot in the second and third sessions. Okay, so before we start, actually, we want to ask the audience a question. I'm going to hand this over to Angela.
All right, so I've just launched our first poll question, and we're curious to know what brought you here today. So please answer one of these, whichever best fits you. So are you new to digital rock analysis and curious to see what it can do? Or perhaps you're already familiar with it, but you want to learn more about it? Or maybe you're just here to win a gift card. That's okay too if you select that. Or maybe there's some other reason you're here. So we just like to get a feel for everyone in the audience and why you've joined us today. So I'm going to give you a few more seconds to answer the questions. And we've got a little over 3/4 of people answering. And in 3, 2, 1, I'm going to end the poll and share the results with you guys. So for the most part, people are new to digital rock analysis and want to learn more, and some are already somewhat familiar. So I'm going to stop sharing and send it back to Aya.
Yeah, thanks, Angela. So this is more or less what we expected, and I hope that you will learn a lot in this series if you're new to this subject. Okay, so I actually have another question. Now we're starting on the subject, but what is digital rock physics? Actually, the term digital rock physics is the one that's often used, and we're naming this series digital rock analysis just because we're focused on the CT analysis aspect of it. But what is digital rock physics? Before I tell you what it is, Angela is going to ask you to guess.
And that's our next poll question. So which do you think it is? Do you think it's the physics about digitally recorded rock music? Or maybe it's analysis of flow properties of reservoir rocks using image-based computation? Or do you instead think digital rock physics is CT image analysis of all types of rocks? So I'll give you a few seconds to answer before we share the results of this poll.
Coming in fast.
They're coming in fast. That's right. We have real close to the last
And it
numbers.
is not overwhelming.
It is not overwhelming. Not overwhelming, but it is split between a couple of options. So I'm going to close the poll.
Yes.
And I'm going to share the results with you. And it's pretty split between the analysis of flow properties of reservoir rocks using image-based computation and CT image analysis. And Aya is going to tell us what it is, and I'm going to stop sharing.
So if you just try to guess what this is from the name, I can understand that people think this is about all kinds of rocks. But actually, digital rock physics is usually this term is used to talk about analysis of the flow properties of reservoir rocks. And we do this analysis using digitally collected images, such as CT images. So for example, let's say that we are going to analyze sandstone. And this is a relatively small sandstone plug. And if you do a CT scan, you get something like this. And if you look into this closely, you will notice that there are very bright regions representing solid. In this case, it's mostly quartz. And you also have a very dark regions representing the pore space. Now, oftentimes in this pore space, you find water, oil, and sometimes gas as well. And if you're trying to extract the oil from this sandstone or any other reservoir rocks, it's important to understand this pore structure. Now, this is a tiny, tiny plug, right? And when you think about an oil well, you're thinking about the scale in kilometers, as you can see in this figure. And what we are analyzing using CT scan is a tiny piece inside of this reservoir rock layer. And you will take a sample out of it and do CT analysis. Now, the kilometers and millimeters, sometimes microns, so those are two completely different scales. However, if you take enough samples from different locations, you will eventually have enough data to plan your oil extraction from your oil well. So that's how the results are used. Now, going back to the tiny, tiny scale, when you think about rocks like this one, there are many parameters you probably want to learn, again, to plan the extraction of the oil from the pore space. And those parameters include things like porosity. You might also want to know the ratio of open and connected pores. And you can also calculate things like absolute permeability, relative permeability, mechanical properties, and forced emission characteristics. Now, those parameters or the properties can be either experimentally measured or you can digitally calculate them. Those are two different approaches to get to the same parameters. Now, I want to compare those two different approaches, just relatively speaking. The experimental approach is, of course, more empirical compared to the digital approach, although we use a lot of empirically obtained parameters when you do the calculations. Now, the second one, and this is the important difference, the experimental approach tends to take a long time, sometimes even years, to get all the parameters you need. Meanwhile, the digital approach tends to be a lot faster, and sometimes you can get all the numbers you need in weeks. Experimental approach tends to be more expensive compared to the digital approach, but I'm not necessarily trying to say that the digital approach is fundamentally better than the experimental approach, because when you do everything with experiments, you probably need to find a way to scale it better, do it faster and cheaper. But the digital approach, which is fast and inexpensive, also needs some validation from experiments. You can't blindly just trust the simulations. So experiments can provide validation to the digital approach, and the digital approach can help the experimental approach by helping them scale better. So those two approaches or methods, they are often combined together, and you need to look at them both. Now, for the experimental approach, we're not going to get into the details of this part, but you would take cores and plugs and actually run experiments to get parameters you want to analyze. In the digital approach, you would use a CT scan and do everything by calculation. Now, if your digital image looked like this, you can kind of tell that this is not a really high quality image. So that means you can't really get accurate results from it. If your image looked like this one, you're going to be probably okay, and you can do all the simulations accurately. Now, when you look at those two images, you can probably tell which one is bad and which one is good. But what exact properties or qualities do we need to pay attention to? So to this question, before I tell you what they are, I will have Angela ask you guys what you think.
Right, so that's the next poll question that I've just launched. So we'd like to know, what do you think are the image properties that we should be considering for this type of digital rock analysis? Do you think we should consider the field of view, perhaps the voxel resolution, signal to noise ratio, or do you think all of these things are important? So we'll give everyone a few seconds to answer. We've got more than half of the votes coming in from everyone. And I'll just give you a few more seconds. That's about 80%. So what I'm going to do is I'm going to end the poll, and I'm going to share the results with you. And
this one is overwhelmingly.
This is definitely. So
overwhelming.
Yeah.
Overwhelming. So the audience believes all of these are equally should be considered. So I'm going to stop sharing and hand it back to Aya.
Okay, that is correct. You've been paying attention. So all three parameters are important. We've talked about those three properties of parameters in the past workshops and webinars, but just to do a quick recap, if this is your CT scan, this example shows 10 millimeters. That's your field of view. And if you look into this image closely, eventually you see those individual voxels. And in this case, it's 5 microns, and that is your voxel resolution. Also, all CT images, especially with the rocks, you see bright and dark areas. And for example, if you look at a profile here, you see this high gray level signal coming from the quartz, and you also have the noise. And the ratio between those two parameters is the signal to noise ratio. For the field of view and the resolution, those are the two parameters. To some extent, you can kind of just pick a number and set the scanning conditions. For signal to noise ratio, you wouldn't be specifying the signal to noise ratio when you start a scan, but this one is related to the scan time. Now, all those three properties are important. But again, let's take a look at a couple of images to get an idea what is good and what is bad. For signal to noise ratio, this is bad. This is too noisy, but this is good. For voxel resolution, this is probably not good enough, but this is pretty good. For the field of view, this one is a little bit more tricky, but this is probably not large enough, but this is large enough. Again, when we see it, we know if it's good or bad. And we will look into more specifics of how you can tell what's good enough. But now for the field of view, we cannot quite say the larger, the better, because when your field of view is really large and the resolution stays high, then you have to worry about the file size. So what this means is we kind of have to balance the field of view, the voxel resolution, and SNR, signal to noise ratio. And the reality is they're in a trade-off relationship. So you have to pick 2 out of 3 to focus on. So what does this mean? How do we select all those parameters? Now, when it comes to digital rock analysis, there are a couple of really good rule of thumbs you can use. So we're going to review them. First, the field of view. So this is a really large field of view. But at the same time, if you use the entire scan or the volume, it's going to be a 16 gigabyte of file. And that's pretty big. And your calculation might take too long. Instead, you could take a small volume out of this scan and use that for the analysis. Then the possible concern is that that volume might not represent the entire volume very well. To see if that's a good representation of the entire volume, you can do the analysis for that volume and do the same thing for another area. And you repeat the process and then make sure that they give you consistent results. And if that's the case, you can go ahead and say that, okay, this tiny cube is my representative element volume that gives you safely representative parameters for your sample. In this case, this is 2.3 millimeter field of view, and the file size is a lot smaller. It's only 182 megabytes. But if this volume gives you the consistent results, you can just use that as your field of view. The definition of a representative elemental volume, REV, or is also referred to as representative volume element. The definition of this parameter is on the volume that gives you consistently trustworthy results. To give you an example, let's think about the porosity. If you plot the porosity you get from a certain volume versus the analyzed volume, you would see a plot like this one. So if your analyzed volume is really, really tiny, you might be just looking at the pore space, like in this case, then the porosity is 1 or 100%. As you increase the volume, you start to see a mix of solid and pore. So you get some sort of porosity, but if that volume is too small, then the porosity is going to fluctuate. So that's not a really representative volume. Eventually, you see steady number, and that's your REV. Now, if you keep increasing the volume, by the way, you're going to see the porosity change again, because you might getting into different regions with different materials of the areas of the rock. But anyway, so this is the REV, and that's all good to know, I think, in theory. But how would I know what the REV is for my sample? So that's the important question when you're planning a scan. So there is a really good study that came up with a good rule of thumb. So the field of view should be about the representative grain size times 5. That's your REV, just roughly speaking. And this is a number the group of Saxena and his colleagues came up with by looking at all different kinds of actual CT data and also some of the simulated models. So this is a really good rule to use. Now, in terms of what this DF, that's an effective grain size. You can see the original definition in Rump's original paper. You can also use empirical data to more or less estimate what that grain size is. And once you estimate the grain size, you will know what your field of view needs to be. So that's a good rule to remember. Okay, so let's move on to the voxel resolution. So again, when you look into CT or SEM, any images, you will eventually see those individual pixels or voxels. And this is a relatively narrow pore space. We call this pore throat. And it's very important to recognize that throat when you do porosity calculation, and more so when you do permeability calculation. So for that particular throat, we probably have more than 10 dark voxels representing that throat. So that one looks good. But this throat is very narrow, and there is probably barely 1 or 2 dark voxels representing that throat. That might not be enough voxels to see that throat accurately. So for the resolution, the good rule to keep in mind is that the voxel resolution needs to be 1/10 of a dominant throat size. And again, this is coming from empirical data in a study of multiple data sets. Okay. So that's for the resolution. The last one is the signal to noise ratio. This one is in a way tricky, but actually an easy one to make a judgment about. This needs to be high enough to segment the image, meaning this is too low of signal to noise ratio data, and this one is a high SNR data. If you simply apply O2 binarization to those two images, you get results that look like these. This is not a very clean segmentation, and the problem is the noise level is too high or SNR is too low. This one looks clean, meaning that this one has high enough of signal to noise ratio. Okay, so those are the 3 parameters or image properties we need to pay attention to. We can set them properly by using the rules we just reviewed. For the field of view, it needs to be more than 5 times the grain size. The voxel resolution needs to be smaller than 1/10 of the throat size. Now, the voxel size resolution and the signal to noise ratio, there is one parameter you can change to increase them both. So how do we do that? Well, for those 2 parameters, you can increase both of them by increasing the scan time. And I will show you an example. This is an 18-second scan with a 50 micron resolution. It looks okay, but this is probably not good enough on so many levels for digital rock simulation. But if you spend 2 minutes, the resolution stays the same, but the signal to noise ratio gets a lot better. After 17 minutes, now you can improve the resolution as well. And in 75 minutes, you can get pretty decent image. So the SNR and the voxel resolution, both of them can be improved by increasing the scan time. Now, there are articles about those 2 parameters in terms of how to optimize them and improve them. And I think Tom can put the links in the chat so that you can take a look at them if you're interested later. So a few minutes ago, I said that the signal to noise ratio, the voxel resolution, and the field of view are in a trade-off relationship. So the question is, we increase the SNR and the voxel resolution. What happens if, just hypothetically, we increase the field of view too? So let's think about this for a minute. So this is a 100 millimeter cube field of view. Let's say we're going to scan this volume with a 1 micron voxel size. The question is, how big is this file going to be? Well, I'm not going to tell you, and I'll have Angela ask you to guess again.
That's our next poll question, as you might guess. So I've just launched that poll. So if you measured with this setting, with these settings that I had talked about, what do you think your file size will eventually be? Will it be 2 gigabytes or perhaps 2 terabytes? Or instead, do you think it'll be 2 petabytes?
So some of you either have thought about this and calculated it, or you've been to one of our webinars.
Perhaps so, yeah. So it's kind of balanced, but we have a
Mhm.
winner
Yeah, there's
leading
a
the
winner.
pack. Yeah, there's definitely a winner now. So we've got about 70% participating. We'll wait a couple seconds for a couple of additional votes. But now I'm going to end this poll and share the results with everyone. So the majority of you think that the file size will in fact be 2 terabytes. So I'm going to stop sharing and Aya is going to tell us what the file size is.
Okay. Well, assuming that it's 16-bit depth grayscale, if you actually do this scan, it's going to be 2 petabytes, which is equal to 2,000 terabytes. Apparently, this is way too big to deal with. I wouldn't even be able to save this file. So this is, one way to look at the problem, but again, you have to pick 2 parameters to focus on, not 3 of them at the same time. Now, when the field of view is small, your voxel can be small, meaning that you can do a high resolution scan. But if the field of view is large, the voxel gets large too. Generally speaking, the rule is the voxel resolution should be somewhere between 1/3000th and 1,000th of the field of view. And the file size should be within the reasonable range if you stay there. Okay. So we just talked about the field of view, the voxel resolution, and signal to noise ratio, kind of how to increase them or optimize them. But when it comes to digital rock simulation or analysis, what does this all mean? So let's connect those 3 properties to the analysis of digital rock on images. As a representative parameter, I want to talk about permeability. So this equation, so K is permeability in millidarcy. This equation connects the permeability to the porosity in fraction and pore throat diameter. Those numbers are 3.8 here and minus 1.3 there. Those numbers were determined empirically on using more than 200 sandstones and carbonate samples data. And you can refer to Thomir's original paper if you want to see how those numbers were determined from curve fitting analysis. And this 2.13, that this is a conversion factor between the entry pressure for mercury to a pore throat diameter. And I wanted to see this equation, show this with the pore throat diameter, because that's something we can relate to the measurement conditions or image quality. Okay. So this is a very convenient equation because this pore throat diameter is related to the voxel size because you need to have more than 10 voxels in that space. If you have general guess about the permeability of the rock you're looking at, and you have an estimate the porosity, you can get this from CT scan too, then you will know from this equation what the required voxel size is. You can decide what resolution you need based on this equation. Another way to look at this is you already have a CT scan, so you have the voxel size, and you can calculate the porosity from that image. Then you will know what the minimum permeability you can simulate based on that image. The convenient way of using this equation is to make a plot like this one. So this is permeability versus porosity, and different colored lines representing the borderline between, okay, your data is good enough area, and no, your data is not good enough for this analysis area. So let's pick 1 micron line and see how this works. So if your sample has 15% porosity and the permeability is estimated to be, or you guess it's about 10 to the second millidarcy, then that data point sits here. And it's above the 1 micron line, meaning that if you have a 1 micron voxel size scan, that scan has enough resolution. If the porosity is 10% and the permeability is 1 millidarcy instead, then that data point is going to sit here. And that means 1 micron is not a high enough resolution. You're going to need something closer to 0.1 submicron resolution scan. So this is how you can use this plot to determine if your scan is good enough or not, as far as the resolution goes. So this table shows general range, reported range of a permeability and porosity for different types of rocks. You can see that the sandstones have a relatively high permeability and porosity, but for example, clay and shales, they're a lot tighter, so their permeabilities are a lot lower. And what this means is, going back to this plot, sandstone data points scatter somewhere around here, and many of them can be analyzed using micro CT images. But the shale data points scatter here, meaning that regular CT scanners are not going to be good enough to look at shale and do this type of analysis. You're going to need electron microscopes to do this. Okay, so let me show you a couple of examples of CT scans, then we will switch to the lab camera and run some scans. Okay, so this is a sandstone Idaho gray CT scan. And this is 10 millimeter field of view, 5 micron voxel size. It took about 2 hours to scan it. And this is a pretty good image. And you can see that this is very coarse sandstone. This is another sandstone liver rock. This one is a little bit tighter, so you need a higher resolution, but you can easily analyze this one using CT. This one, this is also a CT scan, but this is from a shale sample. And even with the 0.3 micron voxel size and 14 hours of a scan, you can see different phases in some of the large pores, but you are missing small pores and throats. So this is not a good enough resolution, and you probably need FIB-SEM to analyze this type of sample. But for the first two examples, the sandstone examples, the Idaho gray data sits somewhere around here. So you can tell that the 5 micron is good enough. The liver rock scan sits somewhere around here. So you can tell that the 5 micron is a little iffy. You might want to go down to 2.5 micron resolution to be safe. Okay, so this is the end of the PowerPoint slide section, and then we're going to move into the lab. And let me get to the point to start a scan. And when we're waiting for the scan to be done, we can start taking some of the questions. Okay, so let me switch to the other camera, which I need to find. There it is. Okay, do you see the machine on the screen, everybody? Okay.
Yes.
So this is a CT Lab HX. This is a benchtop micro CT scanner. Let me go around here. And you can slide open this door like this, and let me move the camera closer so that you can see inside of the machine. So on the left side here, you have the X-ray source, and this is where the filter goes in. And this is a sample stage that has X, Y, Z, and also 360 degrees rotation axis. And to your right, we have a flat panel detector. Now on this system, and this is a general case for many cone beam geometry systems, but the sample stage can get closer to the X-ray source to increase the resolution, or the stage can get closer to the detector to increase the field of view, but also reduce the resolution in that case. Okay. So let's say that we want to scan this sample. Okay. So this is a small plug or core of liver rock sandstone. And let's say that I have no idea how to set the scanning parameters. I just have this sample and I'm going to see how it goes. This one is about a 1 inch in diameter. It's not too big, so it should work, right? So let's take a look at this one first. So I'm going to put this sample. By the way, it's sitting on top of a peak sample holder. I just taped it on sample holder like this. And I'm going to shut the door and let me go back to the computer to set scanning conditions. Okay. So this is where all the scans will be saved, and we can look at them later. And on the left, we see measurement conditions. So we're going to use 130 kV, 123 microamp for the generator with 1 millimeter aluminum filter. And we set the sample size as 25 millimeters and roughly about 30 millimeter high. That's the size of the sample. And I want the software to know the size so that the software can see what kind of measurement conditions I can use. So I'm going to click set. And for the field of view, since the sample is only 25 millimeters, I should be able to use 25 millimeter field of view, right? So let me click this. And you will see the sample getting closer to the source to set the field of view for 25 millimeters. Okay. By the way, there is another camera inside of the machine and you can see the sample from the top as well. Now, let's turn on the generator and take a look at the X-ray image. Okay. So usually those plugs or cores, cylinder-shaped samples are very boring when you look at the X-ray image. You don't see much. But let me make sure that it's centered well, because I want the sample to stay within this blue box, which is the field of view. And let's go to 90 degrees to make sure it's not going to get outside of the box. I think this looks pretty good, maybe a little to the left. I'm just clicking the spot I want to bring to the center. Okay. So if you're happy with the sample position, you can go ahead and start a scan. Turn it off. And I'm going to start a scan. Okay, so while we wait for this one to go, I guess we can take some questions.
All right, so we've had a few come in, and Arn was able to answer a couple of them. I'll
Okay.
address those real quick just to make sure everybody's had a chance to see them. So one of the questions was about GeoDict itself, and whether it's cloud-based or basically a workstation. And so are both desktop workstation-based or cloud-based options. So obviously those questions, you can address some of those on the GeoDict website as well at the Math to Market. So I'd encourage you all to take a look at that if you have additional questions, and feel free to type them. I'm sure Arn will be happy to address any questions about the software. The second question was, and actually there's two that are kind of related here. So one is from Boris, the second one is from Jing, and it says, it's asking, can you specify more about the method of how to find the correct rev? So it's, do I have to find the minimal FOB, which has a similar poor parameters for different samples, compare it with physical experiments, et cetera? And Jing actually asked a similar question of, the 5x grain sizes. Do you recommend kind of testing different sections? And, what's the, so if you can give us just, more, elaborate more on the rev size and making sure that you're getting a representative sample. Just some thoughts on that.
So that's a very good question. You can start with 5 times the representative grain size or mean grain size, let's say. And it's always good to check different areas to make sure that that is a good representation. That's one thing to think about. The other thing to consider is if your computer is powerful enough to do a calculation real fast for that FOV, you can make it bigger. Usually the FOV that's good for the simulation speed is smaller than what your CT scanner can cover usually. So depending on the computer speed, you might want to, you don't need to choose just, exactly 5 times the grain size. It can be always bigger. So as far as the calculation time works, you might want to make it a little bit larger. Okay, the scan is done. So let's take a look. So bear in mind, this is only 2-minute scan. So, you know, you probably can kind of guess it. It's not going to look great, but nonetheless, let me zoom in a little bit. So we can see dark spots. Those are the pore spaces, and some bright spots that are inclusions, but you can tell that the resolution is not good enough, right, for this scan. Now we can spend longer time to increase the resolution, but another thing I want to consider is to reduce the field of view at the same time so that we can increase the resolution and get the reasonable field of view. So let's see if we can change this to maybe 7 millimeters. Then when I tried to go to 7 millimeters, I'm pretending that I didn't know that this message was going to come up, but the software is politely suggesting that we might want to reconsider the sample size. And that's because to reduce the field of view and increase the resolution, the sample needs to get closer to the X-ray source. But our sample is 25 millimeters in diameter, so it's too big to get closer to the generator. That's why the software is telling us to reconsider it. So I'm going to take that advice and reconsider it and pick up a smaller sample. So let me just get this one out and let's switch this to a bigger and a smaller one. Okay. So this was the 25 millimeter sample, and this was a little too big to increase the resolution at smaller field of view. So instead, I'm going to use this one. So this one is only 7 millimeters in diameter. So this one can get a lot closer to the X-ray source. And this is still liver rock. It's the same sandstone, just a different size. Let me put this in and tighten the base. Then I'm gonna tell the software, no, now it is only 7 millimeters. Okay, then change the field of view. So now software can happily change the field of view to 7. And if you look at this from the top, you can tell that the sample is really, really close to the X-ray filter. And we couldn't have done this with the 25 millimeter diameter sample. So now we're at 7 millimeter field of view, and let's run another scan. Since this is a different sample, so let me switch to this folder. Okay. And the sample is roughly at the center, so I think I'm good to start a scan here. Okay. If there are more questions, we can probably take them again.
Okay, so I've got one for Arn because he raised his hand and told me that he wants to answer this one regarding a 2 petabyte data set. It's kind of what can be used in order to adjust your system for that. And so I'll let him address that because I saw him wanting to answer that one directly. So if you want to chime in, Arn.
Yes, thank you for your question. So, of course, if you have such a large data set, you may, of course, apply some, let's say, limiting the range to another scale. So you just compress your images. And of course, if you have already processed your data or your images, the data would be much smaller in geodict in the software after it is segmented. So then you can handle your data much better.
Okay. And then there was an earlier question that, let me see if I can find it here, that was answered regarding, now I can't find it. Here it is. I'm sorry. Converting from 16-bit to 8-bit. So asking if you lose a lot of information. And again, I saw Arn answered that in the chat. I wanted to give him an opportunity to actually make sure everybody got a chance to understand what happens when you do that. So If Arn, if you want to answer that, or I know you know the answer too.
Now go
Either
ahead,
one of you is
Arn.
welcome to answer.
Yes, okay, I can go ahead. So of course, if you adjust the range of your scan, you will get down from 60-bit to 8-bit, which means that you do not have that 65,000 values in your histogram range, but you will compress that image and also the information which is inside of your images to the new range of only 0 to 256. And of course, then you will lose information, and that might make your image processing much harder than with a 16-bit dataset.
All right. All right. Well, thank you, Arn. Aya, your data set's done. Is that correct?
Yeah, the
Okay,
scan
we'll
is
hold
done.
off on the next
Yeah,
couple of
we can take
questions
more
until the end.
questions at the end. Yeah.
Very good. All right.
Okay.
Thank you,
So
Arn.
the scan is done. And in this case, the resolution is a little bit higher. So we want to make sure that the focus correction is done properly. And just to save time, let me make the range a little bit smaller too. And we're gonna finish the reconstruction. Okay. So this was 2-minute scan on the small sample. Before we take a look at this, let's go back to the one we just did. So the first scan we did on the 25mm sample had a 50 micron voxel size. Now with this one, the one we just scanned with a 7mm sample, now the resolution is 14 microns in 2 minutes. This can be a lot better if you spend a little bit longer time. But again, if you zoom into this image, you can see the pore space. Still, this is not a good enough of resolution, but we're getting there. Now, let me keep this image on the side here, and let's compare this to other scans we did before the workshop started. So I have a couple of scans already done on the same sample. And one of them, I spent 350 minutes. Let's take a look at this one. Oops. This was a Idaho gray. Sorry about that. I wanted a liver rock, 380 minutes. Okay. And I have another one, again, the same sample. This one was over 1,000 minutes scan. Okay. Let me get the contrast right. And also let's zoom in a little bit to get about the same scale. Okay. So this is the 2-minute scan with a 14 micron voxel size. And this is the about 6 hours, and this one is even longer. So you can see that the last scan has a pretty good signal to noise ratio and a resolution, and this one is ready to be analyzed. If you have this scan, for example, a little bit noisy, and you just can't do a rescan, and you don't have access to the CT scanner anymore or something, then you can also apply image processing to reduce the noise. And that's something we will look into more in the next episode. Okay, so once you have those scans, you're ready to start the analysis, but it's probably good to evaluate the image quality before you spend a whole lot of time. In Geodict, there's a really convenient tool you can use to do this. So let me close all of them and switch to Geodict. And I'm gonna import one of the scans I collected for this session. So this one is Idaho gray. You saw it for a second before. And this one was collected at a 5 micron voxel size. So let me open this. And I'm not using a liver walk for this part because that one takes a little bit of work to segment it, and you will see it in the next episode. But for now, let's take a look at this Idaho gray scan. And this is a simple O2 binarization. This is original image, and this is the segmented solid part. And this looks pretty good to me. So let's say that we are happy with this and create segmentation. So now the segmentation is created. Let me just close this, switch to 3D. So as Arno was explaining before, we have the original image, which is a huge file in general. But once you define the structure of the rock like this, you can make it look a little bit better. You can just use this and get rid of the original image and work with this a lot smaller file or data set to continue your analysis. Now, once you have this, the rock the model, you can evaluate if the data was good enough to continue to do more advanced analysis on this sample. So to do that one, I'm going to go to GeoApp and go to Digital Rock Physics and Sandstone Quality Control. This is a tool we're going to use to evaluate the image quality. And this tool is going to run 3 sets of analysis to make a judgment on this data set. Now, this takes probably a minute or two. It's not a long time, but it takes a little bit of time. So let me open the one I've already calculated. And this is what the results look like. So in this report tab, you see Rev for the sandstone, and we have more than 6 times larger than the grain size. So this is looking pretty good. And for the voxel size, you have 16 voxels in the throat size. So this is more than 10, so it looks pretty good. Now let's take a look at the plot we were using before. Let me make this bigger. So this plot should look familiar to you at this point because we learned how to read this. And for this particular Idaho gray data set, our permeability and the porosity data point sits here. And this is way above this red line. And this line is representing the borderline between the good and the bad areas for the 5 micron voxel size scan. So you can tell them, okay, this is a very, very good data set to use for the analysis. If this sits somewhere below the borderline, then you might want to reconsider scanning the data again. Okay, so that's all I wanted to show you in the lab today. Let's go back to the PowerPoint slide and wrap this up and take a couple more questions. Okay, so give me one sec. Okay, do you see the slide now?
Yes.
Okay. So those are the 3 things we learned today.
Yep.
Now you know how to assess the required resolution and how to collect the high quality CT images. And in the nutshell, you want relatively small sample and spend a long time. And you now also how to evaluate the image quality before you start the analysis. Now, before we take more questions, there are 2 more resources I wanted to share with you. Again, Tom can put the actual links and URLs in the chat. So one is PetroWiki. This is a good site to see what kind of data people collected in the past. This is a good database for the all the data sets you can look at. And the other one is Digital Rocks Portal. If you don't have a lot of CT scans or SCM scans to practice analysis on, but you want to get started, then you can take a look at this website because they have a whole lot of sample images. You can download the actual images, and most of the images come with the original paper published with the analyzed results. So you can see what people analyze from those data sets, and you can actually get the data sets to do your own analysis. So this is a really good site when you're practicing analysis. Okay, I think we have a few more minutes to take more questions. Okay.
Okay. Yep. So we do have time for a short Q&A. We've had a few questions come in that we can address here. And the first one is from Roger. And we might need to have him send in another part of this question. He's asking, how does the integration time increase the resolution? And so I'm not sure if that is specific enough for you to answer, Aya, or if you need more details.
I understand that question, I think. So let me answer it and see if I get this right.
Okay.
So that's a very good question because it's not obvious, right? Just spending longer time is not going to change your resolution. You change the resolution in the scan condition settings. The reason why those two are related is if everything else was the same, and if you just increase the resolution, that means the X-ray photon counts contributing to one voxel reduces. And when the X-ray photon count goes down, your noise level goes up. So another way to look at it is when you increase the resolution, your noise level goes up. To bring the noise level back down, you have to increase the time as well to achieve the same signal to noise ratio you used to have with the lower resolution. And that's how they're all related. So increasing the scan time doesn't automatically increase the resolution. It's more like when you increase the resolution, you don't have a choice but have to increase the scan time. I hope that makes sense. And if not, you can type in more questions or follow-up questions.
Yep, type in another question, Roger, if that doesn't address it, okay? The second question, actually, I believe is exactly related to this from Joel, and it's kind of which parameter was changed between the 380-minute and 1,050-minute scans of the liver rock. And I believe that was, you increased the resolution. So
the difference between those two particular scans and was only the exposure time or the scan time. Everything else was the same. And they are both 2.5 micron voxel size scans.
Okay. Okay. So that was, so he's asking integration time or number of projections. So
a number of projections. I'm sorry. Yeah.
Yes. Okay. Okay. Oh, okay. Here's a question. Here's a good one that just came in fact, it's is there a rule of thumb to determine the rev size for other types of rocks? This may well be, I'm not sure if Aya or if Arn wants to answer this, for carbonates, for example. Is it the same rule of thumb for 5 times the grain size?
Arn is probably
maybe,
more fit down.
Yeah, maybe I answered this question.
Looks like Arn wants to answer that one. Yeah.
So unfortunately,
please, if you've got something, please.
Yeah, okay. So unfortunately, that does not apply for carbonates as well, because usually in carbonates, you have microporosity as well, which means that you have to simulate, let's say, absolute permeability across the scales. So you have different permeability within that microporosity compared to the macroporosity you will see in your CT scan resolved. Yeah, so you would have to go across a scale and go to the nanometer scale, for example, to obtain a resolution which is high enough to determine the actual permeability of these microporous regions. And then you can go back to your pore scale and insert the values you've determined for the permeability to your microporous regions.
And we will show you guys how to do it in the next, I think in the next episode. Yeah.
Stay tuned for more details.
Stay tuned, right. I have one comment I want to add to the answer I gave you guys about the number of projections. It was misleading. So number of projections in terms of how many angle, spots we use, that was the same between the two scans. What was different was how many frames I added to get one projection for one angle. So it's the exposure time, but it was not a continuous exposure. You would do like a half a second exposure, and you do that for 16 times or 32 times for the same angle. I hope this makes sense. In terms of number of projections for the different angle points, it was the same for those two scans.
Okay. Oops, did a question. Okay. Yeah, and then Roger actually had a good comment, and yeah, I thought this was interesting just to point out. So to get a 2,000 petabyte or a 2 petabyte data set, It would be like having 200,000 pixels by 200,000 pixels as a detector panel. And so I think Roger wants to know, where's that detector and where can you buy one of those?
I want to know that
That's
too.
a pretty large panel, I would imagine.
Yeah, if you
So,
find one, let us know.
Yeah. So all right. So hey, we just hit our hour. So
Oh, yep.
there's a couple unanswered.
Okay.
We'll get back to you with those after the session. All right. So as I said earlier, our recording of the webinar will be available tomorrow, and an email will go out to all participants with instructions on how to review the recorded presentation. The links that were mentioned today, there were a lot of them, will be shared on the landing page as well. So if you didn't get them today, rest assured you'll get them tomorrow. Now, we'll be hosting the second session on digital rock analysis, focusing on segmentation and property analyses on Wednesday, August 17th at 2 p.m. Eastern, 11 a.m. Pacific. That link is also in the chat and will be in the resources listed tomorrow. We look forward to seeing you then. Thank you again for joining us, and we'll talk to you in August.
Thank you.
Bye, everyone.
Bye.
Thank you.
Bye-bye now.